this problem is for you folks to try. It's very similar to what we just did, but I added one part to it. So your function is f of x equals 3 minus 2x. First of all, you're just finding the differential dy for that function. Then you're going to calculate it if x is 1 and dx is 0.05. Okay. Now, part C is the new part. Part of it I did last time, okay? But this part I didn't do. You're asked to compare the value of delta y and dy. That means you need to actually calculate what delta y is. Remember, delta y is just the difference between f of x plus delta x and f of x. So you're going to have to calculate that. Okay. Now, for that, I recommend using a calculator. This is the sort of thing you can do in the homework. You could do on a take-home quiz. This is the sort of thing I would not ask you to do on a proctored exam or quiz when you're not allowed to use a calculator. And I didn't do this in the last video because it's not very enlightening to watch me punch numbers into a calculator. What I'll do is while you work this out, I'll work it out and I'll just write the answer on the board. Okay. So you're going to be using a calculator to get this. You should be able to calculate dy by hand. And they should be fairly close to each other. That's the basic idea. If we set dx equal to delta x, if the horizontal change for the curved function and the linear function is the same, the vertical change should be close. That's, of course, assuming that delta x and dx are relatively small, that we stay close to the point of tangency. We know that if we move too far away, it ceases to be a good approximation. Okay. Then you're asked to illustrate this with a diagram. Now, I did do that in the last problem. I just didn't include it in the directions. So it's going to be similar to what I drew last time. I just make a note that it's also similar to figure 5 in your text. So if you want to refer to that for reference, you're certainly welcome to. Okay, pause the video, work this out. All right, so I've got the answers worked out up here on the board. I think I'm just going to sort of talk through the process. So we were asked, first of all, to just find the differential. Rise equals slope times run, so I know that dy is the derivative times dx. And here I just worked out the derivative. So I rewrote f, since it was a square root, as a fractional power, and then calculating the derivative was a chain rule. So we got 1/2, 3 minus 2x to the negative 1/2, times the derivative of that inside part. Now, the derivative of 3 minus 2x is just a negative 2. That negative 2 I can cancel with the 2 on bottom, and then I just bumped that negative exponent, I rewrote that as a root in the denominator. So we get negative 1 over root 3 minus 2x. Fine if you kept that still written in terms of a negative exponent, but probably a little bit more user-friendly for evaluating in this form. So this is the answer to part A. dy is negative 1 over root 3 minus 2x times dx. And then we were asked to evaluate that when x was 1 and dx was negative 0.05. I just showed you here, if you want to, you can use that evaluation bar that we've been using sometimes. You just need to indicate that there are two things that you're plugging in. I'm fine if you just labeled that dy. If it's your answer to part B, it's clear that it's dy at these particular values. But that is an option for clarifying the difference between the formula and the formula evaluated for particular values. So we just plugged in 1 for x. Notice that makes the denominator root 3 minus 2 times 1 is just 2. So that's root 1, so the denominator becomes 1. So we had negative 1, that's essentially the slope of our tangent line at this point, times dx was 0.05, so we get negative 0.05. Okay. Now, we were asked to compare that to delta y and to draw a picture. I actually drew the picture first because I find the picture helps me to see what I need to plug in. So this is the function right here, root 3 minus 2x. It's defined if 3 minus 2x is bigger than or equal to 0. So it's defined at and to the left of positive 3/2. Okay. Here's our tangent line at 1. Okay. And it had a slope of negative 1. Now, if I'm going to be moving 0.05 to the right of that, that's going to be kind of hard to see here. So what I did is I drew another picture here where I sort of zoomed in on just this part of the picture. Okay. So I drew an axis here, but if I were drawing this full picture, the actual x-axis would probably be out of the picture because I've zoomed in so much. So I'm not claiming that this is at the actual height y equals 0. This is just keeping track of where we are. So if this was the point of tangency where x was 1, if I move 0.05 to the right, that's going to take me to 1.05. And so you can see on the tangent line, if I go 0.05 to the right, I go 0.05 down, illustrating that dy was negative 0.05. On the actual curve, if I go that far to the right, that's going to take me to this point. The amount that I go down, it looks like, is a little bit bigger. But I'm going to calculate that by actually just calculating the y value here, which would be the function at 1.05, and subtracting the y value here, which is the function at 1. So that's what I did here. I said delta y was f of 1.05 minus f of 1. That ends up being the square root of 0.9 minus 1. Now, I don't know that off the top of my head, so here's where I plugged into a calculator, and I got negative 0.0513167, and then there were some more digits too. Okay, but you'll notice we were asked to compare these things. This is close. Delta y is a little bit bigger, consistent with my picture. The function actually decreases a little bit more than the line does, but it's close. So if I wanted to estimate how much this function is going to change from its value at 1, if I go 0.05 to the right, dy of negative 0.05 is a decent estimate of how much the y values actually change.